Thank you. Hello everyone, my name is Youil Kim. I'm from Samsung Research. Today I talk about some of our experience of developing space static analyzer and deploying the tool to Samsung Electronics. This is a co-work with my ISP colleagues. Actually, there are not much technical things in my talk. Instead, I hope you enjoy your success story. First of all, please let me explain some background information. Svace is a static analyzer for early detection of software bugs. Static analysis is a technique to estimate program's runtime behavior without actually executing the program by analyzing the source code, and thus it has several advantages, including that it does not require runtime environment or test input, and it is easily applicable to large-scale software. From my point of view, we may consider it as an automated code review. There is a bug in the code in the picture. A human reviewer may find the bug during he reviews this code. Similarly, we know that a static analyzer can find this bug instead of a human reviewer. I believe that static analysis tools are essential in a modern software development process in order to improve the quality of software and reduce developers' effort. In this slide, I summarize our collaboration history. In 2009, we started a joint project on Svace of ISP. At that time, our initial goal was to introduce Svace as an auxiliary tool in addition to other static analysis tools. But in 2012, we decided to develop Svace as the main static analyzer in our software development process. So we put a lot of time and effort to improve Svace from 2013 to 2015. As I remember, my ISP colleagues also had very tough time during this period. At the end of 2015, we successfully deployed Svace. After that, we improved Svace every year, and we released a new version even in this year. Our collaboration is to be continued in the next year too. Now Svace has been deployed to most business divisions in the company, include these titles. Most of C, C++, C#, and Java source code in the company now is regularly checked with Svace. It includes Tizen TVs, Samsung mobile devices, and Family Hub. More than 10,000 developers in the company are using Svace. And more than 300 billion lines of code has been checked with Svace. Please note that this is just a safe approximation. However, before the success story, we had several challenges. To be honest, I knew that it would be never easy to develop such a tool, but we underestimated the actual effort. This diagram shows a typical high-level architecture of a static analysis tool. There is source code. The build capture module monitors the build process of the source project and recognizes compilation commands and generates the intermediate representation for the code for later analysis. Then the analysis engine analyzes the intermediate representation and generates the list of potential defects. Finally, defect management system helps us to review those defects and manage the history of our actions on those defects. There is no doubt that a good analysis engine is important. However, I'd like to emphasize that the build capture modules and defect manager systems are even more important in reality. In the following slides, I'm planning to introduce some challenges we met at each phase. Let's get started. Let's talk about build capturing first. There are much more issues related to build capturing, but in this talk, I'll focus on C and C++ programs. Let me recall what happened to us when we tried to analyze C and C++ programs in the company. Build capturing is essential because we cannot analyze C and C++ programs without build time information. Svace uses Clang as a C and C++ front end, but we found that Clang was not enough to support all of C and C++ programs we found in the company. Surprisingly, we found more than 90 different C and C++ compilers with its own options and extensions. This is partly due to that various CPUs are used in consumer electronics, and most chip vendors provide their own compilers. In addition, we had to support various systems, including on old legacy systems, because we couldn't build a certain project in other environments. Tigen is the most important target for us, but conventional build capture implementation may not work with GBS and OBS used in Tigen. Here are some achievements so far. Now Svace provides quite good build capture features, as good as those in any commercial tools. We extended Clang so that it can handle most of company code, although we left a small workaround to ignore unknown constructs. To be honest, we still have to modify Clang every year due to some new patterns and new compilers. For Tigen, we made a special IPM package to install Svace into the build root and automatically enable Svace build capture. Let's move to analysis engine issues. At the beginning, Svace was a static analyzer for LLVM bit code. One interesting point is that we realized that IR level analysis was not enough to cover all interesting code patterns because some code patterns may disappear after we translate the code into LLVM bit code. In other words, some interesting coding errors cannot be detected after we translate the code into LLVM bit code. Second, for precision, test-sensitive analysis was essential, but was not enough to satisfy our quality goals. Unfortunately, there is no one silver bullet to address all different post-positive patterns. You will find many weird code patterns that cause false positives, but you never imagined before. Furthermore, some static analyzer warnings are technically true positives from your point of view, but our developers don't want to see them. As far as I know, developing a good analysis engine requires a tedious feedback loop, investigating false alarm patterns, and improving engines, investigating another patterns, and improving engine, and so on. So now Svace has lightweight checkers working on abstract syntax tree. For example, we integrated Clang static analyzer for C and C++ analysis. Svace performs test-sensitive analysis, I believe quite good test-sensitive analysis using SM solver. And in this year, we removed another 47% of false alarms based on developers' feedback. Let's continue with few more analysis engine challenges. Let's suppose that we want to pose a policy that developers should fix all defects detected by Svace. Then analysis result should be deterministic and stable. In other words, if you analyze the same project several times, we should get the same result every time. It means that you cannot rely on hardware timer, random values, and any other non-deterministic components. And please note that a build process is often not deterministic due to timestamp and temporary files and so on. Furthermore, even if some part of a project has been changed, developers expect to get the same set of defects for the rest of the project, I mean unchanged part of the project. Next, I would say the analysis performance is not always enough. Developers expect to get daily analysis results even for the largest code base in our company, but our code base becomes larger and larger. So even if the performance is enough today, it is possible that it's not enough in the next year. And if we integrate Svace into our code review system, developers even expect to get the analysis results within several minutes. So far, some achievement is like this. It takes 11 hours to build and analyze our Tizen 5 project, which is 17 million lines. And Svace produced the same result when we analyze the project 5 times. Let's talk about defect manager system. Even if we resolve all the challenges so far, it's not enough. It's crucial that having a good defect management system, some of the key features of such system will be support for code navigation and grouping similar warnings and remembering our actions on some defects. It requires considerable effort to develop such system as it should handle a lot of data. Also, it requires some help from static analysis engines. Now, Svace provides some necessary information for such defect management system, including warning grouping factors and code navigation information. For several years, we developed our own defect management system and improved it. The picture shows our defect manager systems. How does it look like? There is one more challenge that is not a technical one. As you know, there are good commercial tools. So we should keep our competitiveness against the commercial tools. We are striving to keep our competitiveness against commercial tools by meeting the company-specific requirements better and by tight integration into our software development infrastructure. There are some examples. In 2015, we provided Svace for an old legacy system that a commercial tool already stopped to support it. In 2015, Svace enables an analysis of a new Android system using Jack toolchain 6 months earlier than any other commercial tools. Also, Svace has a lot of checkers which are developed by the requirements from our business divisions. Even though we had many challenges, so far the conclusion is that we successfully deployed Svace into the company through active collaboration with ISP members. In addition, we integrated Svace into our software development infrastructure. In the next two slides, I'll introduce Analysis Hub and Code Review Board briefly. In short, Analysis Hub provides Svace as a service inside the company. Code Review Board provides Svace result as an automated code review command. We have developed Analysis Hub, which is an extensible framework for providing static analysis as a service. In the picture, our developer can request a static analysis on his code through our website, and he gets analysis report after some time. As you can see in the picture, Svace is now one of the core analysis engines in the service. On top of Analysis Hub, we developed code review board. It generates automated code review comments, including Svace analysis result. On the left side, you can see that we provide Svace result for our Tizen garage system. On the right picture, you can see that we provide Svace analysis result for a project in our GitHub Enterprise server. This is the last slide. Our collaboration is to be continued in the next years. Of course, we have some ideas on future work, including AI for code analysis and other intelligence services for our developers. And we hope to extend our collaboration to other areas as well. Here, I drew our collaboration area among my personal interests. That's it. So if you have any questions, I will welcome.
Okay, let's thank the speaker and we'll be accepting вопросы, пожалуйста.
Hello, thank you very much. Could you open slide 7, please? Yes, yes, thank you. You have noted that some errors could not be detected after translation into bitcode. Could you give some examples, please?
There are some examples. The question is, what is the example of coding errors that cannot be detected in bitcode level?
Yes.
A typical example is the misuse of size of expression in C and C++ programs. We found that size of expression is translated to some numbers, or already translated to some numbers in LLVM bitcode. So we could not detect the misuse of size of expression in LLVM bitcode level. Another example is the misuse of macro. We cannot analyze macro uses in LLVM bitcode level.
Sorry, what is
macro?
Okay, yeah. Thank you. And next slide, please. You have mentioned that your new build process become deterministic. Yes, have you patched all your build systems or used some new build system to make deterministic builds?
The question is that if some build system can be deterministic, then did we patch our build system to show deterministic behavior? Is it right?
Yes.
We didn't do anything for our build system, but thanks to our colleagues' work, now Svace shows stable results, even though the non-determinism in the build system.
Okay, thank you. And last question on slide 13.
13. Here.
Next, please.
Next.
So, do I understand correctly that Svace will be integrated with GitHub in some time?
I don't mean public GitHub. I mean GitHub Enterprise installed inside the company.
Okay, thank you very much.
Okay, any more questions?
Hello, thanks for the talk. Can you please switch to the next slide?
Next slide. This one?
Can you please say a few words about automated program repair service? What is it? What does it do?
Automated program repair.
Yeah.
Our goal is to reduce code writing effort of developers. There are many areas titled automated program repair, but we started with a small goal. We started work on automated bug fix, those detected by Svace. Now Svace can suggest how to fix code to fix bugs detected by some space checkers. As I remember, we made autofix picture for 12 or more checkers in space, and this is just a start, and we plan to extend this work further.
Thank you.
I think we have time for one more question. Yes, just. Okay, and you two more.
As far as we have 11 hours for Tizen check, how do you use it? Do you use it at night, or how it is used in a regular process? As a night build or a weekly build?
Yes.
Do you have plans to have some checks for each commit?
We have several policies for analyzing Tizen project, but when I mentioned 11 hours, it is time for the full analysis of whole Tizen, and we perform this kind of analysis at night. So it's about nightly analysis. But if the developers want to verify some of their picks more quickly, then he or she can analyze a single Tizen package without analyzing the full Tizen code. So we provide several options.
Okay, so one last question and we'll take the remaining offline.
Thank you for your talk. Can you please go to slide number 7?
Seven. Okay.
Yes, so right here you separate useless alarms into two categories. It's won't fix and false alarm. Like false alarm, it's we can all understand it, but what is won't fix? It is still error, but it is not critical in this part of code, and how a developer determines that this error is a won't fix error?
Yes, the question is how I distinguish false alarm and won't fix cases. It's somewhat difficult to answer this question because someone has different offline discussion.
Okay, thank you very much.
Okay, let's thank the speaker and thank you, Youil.